Hello and welcome to this video lecture where we will introduce the concept of conditioning, a concept of paramount importance in probability, statistics, and estimation theory. We ask, what is the probability that a person develops prostate cancer given that they are male and smoke? What is the probability that a student scores at least 90% in the exam given that they study for 1 hour every day? What is the probability that a person has COVID-19 given that they have fever? And what is the probability that a person has fever given that they have COVID-19? These are conditional probabilities. A conditional probability is the probability of one event occurring given that another event has occurred. This is how we denote these probabilities. Given a probability space omega fp and two events A and B, where the probability of B is not equal to 0, the probability of A conditional on B is defined as the probability of A and B happening, or what's the same, the probability of the intersection of A and B, divided by the probability of B. If conditioning on B does not alter the probability of A, then we say that A and B are independent events. They are independent from one another. If A and B are independent, it follows that the probability of their intersection is the product of their probabilities. This follows from the definition. Here's an example. Suppose there is a 5% probability that a person has fever and a probability of 3% that they have COVID-19. Of course, one can have COVID-19 without fever, fever without having COVID. Suppose that the probability of having COVID and fever at the same time is 1.5%. We can determine the probability that the person has fever given that, or conditional on the fact that they have COVID. In other words, if we are told that the person has COVID, what is the probability that they have fever? Following the definition, we can see that this is 0.015 over 0.03, which is equal to 50%. But if a person has fever, what is the probability they have COVID? The answer turns out to be 30%, again following the definition. We have defined a conditional version of the probability of an event conditioned on another event. We can also define the probability of an event conditional on the outcome of a random variable. Here we will work on discrete probability spaces where things are easier. Let's start with an example. We roll a fair die and we play a game where the winnings are £0 if we roll 1, 2 or 3, and £1 if we roll 4, 5 or 6. If we know that someone has won £1, the probability they rolled 1 is 0. The probability they rolled 1, 2 or 3 is 0 quite clearly, and the probability they rolled 4, 5 or 6 is 1. We ask, what is the probability that the outcome of their roll is inside the event A, given that they have won £1? This gives rise to the notion of the probability of an event conditional on the outcome of a random variable. Note that for every event A and real number x, the probability of A, conditional on the fact that the random variable x equals x lowercase, is a probability value. This means it's a value between 0 and 1. The definition is quite straightforward. For an event A, the probability of A, given that the outcome of the random variable x is known and equal to x lowercase, is the probability of the event A conditional on the event B of x lowercase. And we know already what it means to condition an event on another event. Here, B of x is the set of all omega, the set of all outcomes of the random experiment, such that the random variable x at omega is equal to x lowercase. Let's go back to the previous example, where we win nothing if we roll 1, 2, or 3, and we win £1 if we roll 4, 5, or 6. According to this definition, the probability someone rolled either 1 or 5, given that they won £1, is the probability of the set that contains 1 and 5, given the event that omega is in the sample space omega, such that x of omega is equal to 1. This is the set indicated here in red. We know that one wins £1 if and only if they have rolled 4, 5, or 6. Using the definition of conditional probability, we find that the result is 1/3. We have described and defined a conditional version of the probability. We can do the same for the expectation. Let's first try to understand what the conditional expectation is. Let x be the temperature in Belfast. The expected temperature is 13.2 Celsius. However, if we know it's July, we should expect a temperature of 19.3 Celsius. One more example. The expected value of the height of a 19-year-old person is 1.71 meters. But if we know they're Dutch, the expected value, conditional on being from the Netherlands, is 1.77 meters. If additionally we know that they are male, the expected height becomes 1.83 meters. Let's see now how we can use the conditional probability to define the conditional expectation on discrete probability spaces. We start with discrete spaces because things are easier there. Firstly, let's recall how we define the expectation of a random variable on a finite probability space, let's say omega, which contains the elements 1, 2, 3 up to n. The expectation of a random variable x is the weighted average of the values of x with the probabilities. Note that here xi denotes the value of the random variable x if the outcome I occurs. To define the conditional expectation of x on an event A, we replace the above probability by its conditional counterpart. We can now invoke the definition of the conditional probability that we stated previously, which is the probability of the intersection of the set that contains I with A divided by the probability of A. Now I either is in A or it isn't. If it is, the intersection is equal to the singleton that contains I. If it isn't, the intersection is empty, so the probability is 0. This allows us to obtain that the probability of I conditional on A is the probability of the singleton I divided by the probability of A if I is inside A, and it's 0 otherwise. If we plug this back into the definition of the conditional expectation of x given A, we see that it is 1 over the probability of A times the sum of xi times the probability of I. And the sum is taken over the elements I in the set A. So this is the definition of the conditional expectation of x given A over a discrete probability space. This example will shed some light on how we can determine a conditional expectation. Consider a fair die and suppose that you win -1 to the power n times n pounds whenever you roll n. To put it simply, this means that if you roll 1, you win -1 pounds. This means you lose 1 pound. If you roll 2, you win 2 pounds. If you roll 3, you lose 3 pounds. If you roll 4, you win 4 pounds, and so on and so forth. Let x denote exactly your winnings. This is a random variable, x is a random variable on the familiar probability space of a fair die. then the expected winnings can be found to be 0.5 pounds. Now consider the event 2, 4, 6. This means you roll a die, someone looks at it without revealing it to you, and they inform you that you've rolled either a 2, a 4, or a 6. The probability of A is of course 1/2. Using the equation that we stated previously, we see that the expected winnings conditional on A become 4 pounds. In this example, we see once again that the additional information can change the expected value of a random variable. Like we said before, that the temperature in Belfast is 13.2 Celsius. But if we know it's July, the expected temperature becomes 19.3 Celsius. It can change quite drastically. There is an alternative way to write the conditional expectation of a random variable. Suppose again that omega fp is a probability space and omega is a finite set, and take x to be a real valued random variable that takes m different unique values. We denote these values by x1, 2, 3 and so on, where the index, you see, the subscript is in parentheses. It may happen that the same outcome of the random experiment, the same outcome from omega, from the sample space, corresponds to the same value of x. To link the previous example with the die, it may be that two different outcomes of the die correspond to the same amount of winnings. The expectation of x can be written as this sum, where we traverse the m values of x, the m unique values of x, and we multiply by the probability that x equals each value. To derive the expectation of x conditional on the event A, we just need to condition these probabilities on the event A. This is just an alternative way to express the conditional expectation of a random variable, and it is equivalent to what we stated before. The expectation of a random variable x on a discrete probability space can be conditioned by another random variable y on that space. This is the expectation of x given that another random variable y is equal to a certain value y lowercase. Look here, y uppercase is a random variable, so it's a function. Y lowercase is just a number. Note that in this definition we have the probability of an event conditional on a random variable. This has been defined previously, and essentially this is conditional on the event of all omega in the sample space omega, such that y of omega is equal to y lowercase. This conditional expectation is a function of the value y lowercase. So a conditional expectation is a function. You give y lowercase and you obtain the conditional expectation of x. The conditional expectation can be seen as a random variable if we don't know the outcome of the random variable y. So let's be more specific. If we replace y lowercase by y uppercase at omega, which is a particular outcome of the random variable, the expectation of x conditioned on the event that y is equal to y of omega becomes a function of omega, and as such it is a random variable. For different outcomes omega of the random experiment, we will have a value of this conditional expectation. The conditional expectation, seen as a random variable, is denoted by E, expectation of x, given y uppercase. So whenever we write expectation of x given y uppercase, this is a random variable. We have to conduct a random experiment, observe the value of y, and then given just this information, we can determine the expectation of x given y. So this notation implies that a particular random experiment has not been conducted, so the die has not been rolled yet. Lastly, note that the expectation of x conditioned on the fact that y uppercase is equal to the value y lowercase is essentially the expectation of x conditioned on the event A of y, So this is like a function that you pass a value y and returns an event, a set. So this is the set of all omega, such that y of omega is equal to y lowercase. However, beware of the fact that this makes sense only on discrete probability spaces. The reason for that is that in continuous spaces, the probability of a of y is 0, and we cannot condition a random variable on an event of probability 0. In the next video lecture, we will see what happens if we have continuous spaces and continuous random variables. So thank you very much for watching, and until next time, goodbye.